Here, the value of r squared, when we take our correlation coefficient and square the value, it tells us something about the proportion of the variation in y that can be explained by the linear relationship between x and y. And so oftentimes that'll be one way that we can interpret this value of r, is telling us roughly what proportion of the data is explained by that linear relationship. And then below here, one thing we need to keep in mind is that different samples will produce different scatter plots, and thus different R values. So our goal here will be to take large samples and try and get close to our true linear proportion, which is looking at the sort of population parameter, rho. So this is the Greek symbol rho that looks at the true linear correlation coefficient for the population. And our goal here is to use R as a way of estimating rho. And so what we can do is we can do some hypothesis testing with our sample statistic R, and use that to determine whether or not there's a correlation. In other words, we want to do hypothesis testing with some assumption about rho. So when we're going to assume that there's no correlation, we're assuming that rho is equal to 0. And if we're doing a hypothesis test, then we want to try and prove otherwise based on our coefficient R that we've computed from our sample data. So here is the basic process, like any hypothesis test. In this case, we're always going to be assuming that our null hypothesis is that our correlation coefficient, our population correlation coefficient, is equal to 0. In other words, that means that there's no linear correlation. And the alternative hypothesis will always be that that correlation coefficient is not 0, and hence there is a linear correlation. But we should point out that in order for us to really conclude that there is a linear correlation, rho needs to be relatively far away from 0. And how far away it needs to be from 0 depends on our significance level, which again we'll denote by alpha. So based on that significance level, we want to then compute our test statistic to see where that compares with a critical value that we can calculate from the significance level. Now I'm gonna mostly focus on the critical value method here, as opposed to the p-value method. In the past, we've always done p-value method for hypothesis testing because it was convenient to use our calculator to compute the p-values. At this point, though, it's going to be helpful to think about the critical value method in this case because it tells us sort of a range of values of R where we would expect to see some sort of correlation. So when we compute so remember, this is our level of significance, we can find a critical value for this level of significance, and that'll tell us some value here and the negative version over here. And then we compare that with our test statistic. If our test statistic falls in, say, this region here, or in this region here, then we can conclude that there is a correlation. So in other words, here, if our test statistic falls in this region here, then we're going to reject the null hypothesis, and we'll say that there is a a positive correlation. Versus over here, if our critical value falls in this negative region over here, beyond the critical value, then again here we're going to reject the null hypothesis and say that there's a negative correlation. Okay. On the other hand, if we get a p-value, or sorry, if we get a test statistic that falls in this region here, this will be no correlation. So here we're going to fail to reject, and so there would be, we would conclude that there's no correlation. And in this table here, we can easily see what those different critical values would be based on either a significance level of 0.05 or a significance level of 0.01, and the varying sample sizes here. So for instance, if I had a sample size of 10, I had 10 pairs of data, and I wanted a significance level of 0.05, then I would look for values of R that are either greater than 0.632 or less than negative 0.632 in order to say that there's a correlation. So we'll use this table when we're making our conclusion about whether to reject or fail to reject. On our calculator, we can use the lin-reg t-test to help us compute the test statistic. So if you go to your calculator, go to Stat, Tests, and then towards the bottom you'll see the lin-reg t-test. And notice that it takes as an input, it takes 2 lists. So what we'll need to do is we'll need to enter all of the data into 2 lists. So we have an X list, which can be one list, and a Y list, which will be another list. So we're going to enter all the data for the X and the Y coordinates of our scatter plot into 2 lists, and then when we run the lin-reg t-test here, it's going to output a couple things, but the stuff that we're going to most likely want to take a look at is it'll give us an R value, an R coefficient. Okay, that'll be important. And it also, you'll notice it also gives us a line. So it gives us the line of best fit. Which we'll look at how this is going to be used in the next section. In 10.2, we'll look at how we can use the line of best fit to help us make predictions. But for now, we're focusing on getting the R coefficient, the correlation coefficient, to help us determine whether or not there is any correlation at all.